All right, section 3-2, we're going to talk about the structure of the atom. And when we talk about this section, we're basically going to talk about the history of how the atom went from this solid block of material that Dalton thought it was to the atom that we think of today with protons and neutrons and finally electrons spinning around it. So that's which is called the nuclear model. So in order to do that, we have a couple objectives which we need to discover, which is basically describe how the cathode ray tube led to the discovery of the electron and its properties. So the cathode ray tube led to the discovery of the electron. And the second one we need to look into is that we describe Rutherford's experiment and how it led to the discovery of the nucleus and the atom's properties. So those are the two big ones, okay? All right, next. Okay, so the next slide, discovering the electron in 1897, and that's a good perspective. Before 1900, a gentleman by the name of J.J. Thomson, it says, used the cathode ray tube to deduce the presence of a negatively charged particle, which he called or which eventually was called the electron. Now, just to give you an idea, the cathode ray tube right now are the old tube TVs. So you might have one of these tube TVs in your house. It's basically it's a non-plasma TV. It's a non-flat screen TV. They're kind of big and they're very heavy. Now, as far as the cathode ray tube goes, I had a good picture of it, but the internet isn't working or it's going a little slow. So what we have is this is a cathode ray tube, and this is the stand that it stands on, and it's got electricity. And here's the plug. That's a plug. And it has a piece of metal which is called the cathode. We'll label it as C. And we have an anode, which we'll label as A. And when the electricity was turned on, a beam of light was seen to go from the cathode to the anode. And this cathode ray tube, or the cathode, was basically anything or any amount of matter produced the same exact cathode ray. Now, the cool thing about this cathode ray is that the particles seem to behave differently than regular light. If you would take a magnet and hold the north side of a magnet up to this thing, and the thing would bend away from the magnet. That was curious. And then they took it and they put the south side of a magnet, and it would bend towards the magnet. So light doesn't act like this. Light doesn't bend its particles or its shape based on magnets. So this was something completely different, and they started to look into this thing, this cathode ray. And what they found through these different things of Thomson's cathode ray tube, they found three things. Number one, the particle, the beam of light was negative in nature. Okay, we know this because it was either attracted to or repelled away from a magnet. The second thing, they did some experiments, was that it had mass. Okay, this thing was able to move little paddle wheels and stuff like that. I'm not going to get into that. But the third thing, and probably the coolest of all the experiments, was that all matter seemed to have these negative electrons. These negative electrons, in other words, what they did was, as they set up their cathode ray and they set up the cathode and the anode, they applied aluminum, they applied copper, they applied, you name it, all sorts of different cathodes, and they ended up getting the exact same thing. Okay, so it doesn't matter what happened, all the particles seem to have these electrons. So the electrons turned out to be a very generic particle that all matter, all elements had. So that's a big deal. All right, next slide. Once they find the electron, they know it's negative. But they want to know now, how big is the electron? How much charge does it have? And that's Millikan's oil drop experiment. And what he basically did, and actually this is about 1908. In 1908, Robert Millikan determined that the mass of the electron was about 1/2000th the mass of a hydrogen atom. Now we compare it to a hydrogen atom because a hydrogen atom is the smallest atom that we know of. And so therefore, the electron is so small, it's 1/2000th or 2,000 times smaller than the smallest atom we know of. And we know that it has essentially 1 unit of negative charge, which we're going to abbreviate. It's actually so many thousands of coulombs and stuff like that, or so many fraction of a coulomb. We don't need to know about that. But basically what I want to show you is that Millikan's oil drop experiment worked a little like this. He had this big chamber, and in this chamber he had one of those old style perfume sprayers, and it sprayed oil drops out. And as these oil drops descended, they would fall through a single tiny little hole here. And so we would have this stream of oil particles coming down. Now what he did is this plate was positive and this plate down here was negative. This set up an electrical field. And he had a dial here, there's a knob, and he would turn the dial up, and as he turned the dial up, these particles would then float up. And as he turned the dial down, these particles would float down. So he adjusted this dial just right to make the particles sit right smack dab in the middle. And as it sat in the middle, he was able to read this dial, and he realized that because he knew the electrical charge and he plugged it into these fancy equations and all sorts of things, he was able to determine that the charge, the charge of the electron. And he was able to get the same number almost every time. So he concluded that the charge of the electron was -1. All right, now that's important. So now we know, back on this slide, that the mass of the electron is 1/2000th the mass of the hydrogen atom, which is very, very small. You can see it right here. And the charge of the atom, electron, is -1. Okay, next. So conclusions that we get from the study of the electron. Number one, this first point says what we've seen before, that it doesn't matter what you use. All elements contain these identically charged electrons. Electrons, again, like I said before, are generic particles. The next thing we know that since atoms are electrically neutral and we found a negative particle, what do we have to look for next? If they're electrically neutral and we know we have a negative particle, we have to find a positive particle. So we're going to look for protons. Protons are being looked for next. Okay? And the last point down here, let me move this. It says that electrons have so little mass. Again, they're really teeny tiny. They're about this big. It's not working for me. They're about that big, and the atom is 2,000 times bigger than that. So, since atoms are so massive compared to electrons, what is accounting for the mass of the atom? So that's what they're looking for. So here they're looking for protons, which are pretty massive, right here, and here they're eventually going to look for neutrons, which we of course know do not have any charge to them, but they are quite massive. They're a little bit heavier than protons. Okay, next. Okay, so what we have is they still can't get away from this solid particle. Again, Dalton said that atoms were these solid particles that had that were indivisible. Well, we still have a solid particle here in what's called the plum pudding model, and this is a British thing, so I have no idea what plum pudding is. Okay. Okay. So we have this plum pudding model here, and as we have the plum pudding model, what they thought is, again, this is a sphere, and it has this positive jelly-like substance is what they kind of described it as, and these electrons are kind of like raisins stuck in the plum pudding, just essentially just flying around doing their thing. So that's the plum pudding model. So we still have this solid, indivisible sphere. All right. Next comes Rutherford's gold foil experiment, which was roughly about 2 to 3 years later. And what he did was, and what he found was, let's talk about what he did. He started off with this alpha particle emitter. And the alpha particle emitter shoots these positive particles at this piece of gold foil. Now, this piece of gold foil is a very, very thin piece of gold foil, only 200-300 atoms thick. And what he found was 3 things that astonished him. The first thing, and you would expect that if you would shine a beam of light or energy at any type of shiny surface, you kind of would expect it to bounce or reflect. Most of the particles went straight through. Second, some fraction of the particles were deflected off their path just slightly. They were slightly deflected off their path. Third, some of the particles, as they hit the gold foil, bounced straight back at their source of the alpha particle emitter. So those are the 3 results that he found. So we need to come up with some conclusions. The first conclusion is that, and you're going to see this in the next slide, but since most of the particles pass straight through, we see that an atom is mostly empty space. An atom is mostly empty space. Most of the particles went straight through. Second of all, some of the particles were slightly deflected off their path a little bit, and that means that this nucleus is what they eventually called it was positive. Alpha particles are positive, so therefore it's like putting two north sides of the magnet next to each other. You get them close and they just kind of bounce away from each other. That's what these things were doing. They were getting close to the positive source and they bounce away from each other. And the third thing that they found was that the nucleus was this heavy, dense, massive region, thicker than more powerful and more dense than concrete and steel combined. As we see this thing hits this nucleus and bounces away, and as it does so, it's hitting this impenetrable wall, it seems. So those are the three things they found based on that, so we can come up with some conclusions. Before we do that, we can just talk about the relative size of an atom. If the nucleus were a grain of sand, the entire atom would have a diameter of 5.5 football fields, and that's again with nothing in the middle except for these tiny little highly mobile electrons. So it's very, very small. So when we get to Rutherford's conclusion, the first conclusion we come up with is the atom is mostly empty space. Okay, most of the particles went straight through the gold foil. The second thing we see is that all the positive charge and almost all of the mass is concentrated in this small area called the nucleus. So with this nucleus, this is the massive area. Very massive, very heavy, very dense. And the nucleus is composed of protons and neutrons. They make up the nucleus, and of course we know that the nucleus is in the middle. Okay? The fourth thing, electrons are distributed around the nucleus and they occupy the volume. So if we want to talk about the mass of the nucleus, we're going to talk about the nucleus, which is protons and neutrons. If we're going to talk about the volume of the atom, we're going to talk about how they have electrons or something called an electron cloud. Okay? And lastly, once we're done with this, we end up with the model called the nuclear model. Okay? So if you guys were missing today or you just need a review, there you go. That's section 3-2.